I guess we are back working. Sorry, my computer decided to reboot just a minute before, so I had to restart everything. All right, guys. So how's everyone doing? Any questions before we get started? Let me share my screen, and we will get going. All right, guys. So what I have done, right? Last week the assignment was random forest and boost trees, right? So the idea is take the same. So I'm looking at the welcome document, guys, right? So you guys know the link already. So let me just put this link right, just in case. All right, it's my chat window. Okay, so you guys know this by now. Anywho, so what I'm doing right now is, so last week the idea was take the exact notebooks you guys did for decision trees and then port them over to random forest, right? And the idea was just to illustrate how easy it is to plug in random forest, right, for decision trees. And so how did that go, guys? Any questions or comments on that? Anyone had any issues substituting random forest to boost trees to the decision trees? Okay, so I just opened up the class submissions folder. So let's take a look at, anybody has a notebook I can look at? I would appreciate it. Anybody has done the notebooks? Cool, I see lots of submissions. Vasilios, can I use yours? Yeah, all right, let me pick yours.
It's half-baked.
That's okay, yeah. So again, so I randomly pick everybody because we want to how do you say, we all learn from each other, right? So I'm not, so okay, I'll go with your random forest notebook. So let me open this up. You guys can see my screen okay, right? Yeah, okay. So let me make a copy in case I need to make any modifications. And this is something I recommend to you guys, when you view other people's notebook, right? Just make a copy. This way, any changes you guys make will be saved. Okay. So cool. So let me say, okay, I know you were looking at the COVID case. That's very good. Okay, so let me look at the data. Interesting. Huh. And is what is the prediction here? Is it a regression? COVID, Vasilios?
Yes, if based on the data we have and the symptoms usually, if it is a case that can lead to death or not. So if they have to put them into the intensive care or not.
Oh, okay. So a classification problem, right? Okay, gotcha. Like a yes or no kind of a thing. Okay, very good. And this is another thing I want you guys to get confident is basically when somebody tells you a problem, immediately we should say, okay, yeah, this is a classification problem. It's a binary classifier or multi-class classifier, right? So that level of confidence, I want you guys to build up, right? So again, the way I sort of approach this machine learning is a little different because a lot of the time people can obsess over the algorithms. Which algorithm should I use, right? So, but I say, look, the algorithms are pretty simple, right? If you look at this, like things like scikit and deep, TensorFlow, they already have all these algorithms implemented. So just knowing them how to use this, once you know one, you know how to use the others, right? So don't obsess over the algorithms, but I want you guys to do is like to build up the confidence. Okay, so this is the problem. Okay, well, is it a balanced data set, unbalanced data set, right? How do we predict and all that, right? So very good. Okay, very good. Good. So, yep. So again, all this stuff, right? And this is something I was teaching this class last week, and there were some data scientists who knew some machine learning and they want to know some algorithms. But a lot of the times, they were basically getting stuck in this data prep tasks, encoding variables, scaling variables, right? And they're not exactly machine learning, but you need to sort of understand this so you can go and apply the algorithms, right? So that's why the data sets I'm actually recommending to you guys now, they have categorical variables, right? Because you need to kind of get this, just get this down. Okay, so yeah, categorical variable, how do we encode them, right? So label encoder, right? You're using this, very good. Okay, good. Okay, so where are we? Okay, there we go. So basically, we extract X and Y. How interesting. Okay, so gotcha, X and Y, right? So again, keep this process, again, to me, this is mentally easy for me. I'm like, whatever modification I want to do in the data, I finally want to get to my X and Y, right? All the data manipulation is done before that, right? So once I have X and Y, then you guys know the rest, right? Split, right? So the random forest classifier right here, right? And then, so now, right? So again, when you guys are doing the first time, okay, so take a look at this one, right? So what are the important parameters? So this is pretty much the only parameter you need to specify, number of estimators. So what is it, like number of trees, right? I think in the default, you can actually use random forest classifier, and the default value should be 50 or 100. Let me see. Right, random forest classifier, yeah, number of estimates is 100, right? So you could just say random forest classifier with all the default values, right? And also, now you can say, okay, what is Gini, right? We understand what a Gini means, right? Again, the default values are pretty sane, right? So, and we know what the max depths and all the stuff, right? So you can configure, tweak this a little bit, but for the most part, you can just pick the random forest by default values. But very good, yeah. So, and I see you're setting the random state just so we have predictable results, very good, and minimum sample if, yeah. So that means like if the leaf has right 5 nodes, do not split, right? So good, that's it. And then once you get the initial model fit, right, we got that, right? And also now we know a little better, right? Because here we are fixing random state just to kind of get a baseline idea. But then what we do is we do cross validation. So this should be automatic by now for you guys, right? Any algorithm you guys choose, right? You want to do like cross validation, right? And you can just a couple of lines of code, and at this point you want to just do the score, and then how many splits, right? Was it 10 splits? Yeah, right. And that's it. Okay. So with cross validation, it'll basically tell you, right? What they, remember, it will give you a range of accuracies, and you want to take the mean. And sometimes people take standard deviation just to understand, if there's a big variance, right? But random forest should be fairly stable, because remember, the whole point of random forest is to what? Stabilize the decision trees, right? So it should be fairly stable. Very good, yeah, cool. Okay, that's very good. So are you really getting 98% accuracy? Wow, okay. That's pretty amazing. Okay. And then, is this feature importance? Yeah. Okay, yeah, so that's what, okay. So this is something important that you guys want to understand. Random forest, and this is a very nice idea, has an attribute called feature importances. What does it mean? Is that model basically says, to construct the model, these are the important features, right? So every attribute, and it'll give you like a percentage. I think they should all add up to 1, I believe. Yeah. So every attribute, it will say, okay, how important was this attribute for me to make the decision? And so, for example, right, and if you do like a little, how do you say, sort by the highest, like probably I see summary meaning 32%, location 19%, right? So these are pretty important. Age 12%. I mean, yeah, right. I mean, I know very little about COVID, but from what I can say, the feature importance makes sense, right? Because age is very important, right?
I can tell you, I had another idea, but I didn't have enough time.
Yeah.
The actual symptoms are actually having a lot of mixture of words.
Oh, I see.
So I would love I would love to have a little bit more free time, for my work to actually split the symptoms into, say, one hot encoding thing.
Very good.
I'm trying to see which actual symptoms are actually the most, serious in the case of evaluating the problem.
That's right. That's right. Oh, okay, I see. Okay. Oh, okay. So like symptoms, they have like a comma, something like they will say like headache or something like this. Is that right? Yeah. Interesting. Okay. Okay. Interesting. Okay. Yep. Yep. So again, a lot of the times, and you are right, a lot of the times, right, a lot of your work would be done before X and Y, right? Because once you have X and Y, right, you've pretty much chosen your input and output, right? So kind of keep this in mind, right? All your data manipulation, feature engineering, everything happens before X and Y, right? Anyway, so just, yeah. So, and now you're starting to understand, right? In machine learning, what's important is understanding data. Because algorithms, right? Once you have a fairly good idea of one algorithm, the algorithms are pretty straightforward, right? And that's why we sort of built up towards it, right? We kind of wanted to make sure, okay, what's the algorithm, right? And we didn't want to know, okay, so why we are doing cross-validation. So now we have all the basic concepts under our belt. So now we should be able to evaluate the algorithm pretty quickly. Yeah, very good. But I'm still impressed. Yeah, 90% accuracy, and that is a pretty, I would imagine we're a pretty complex data set, right? Yeah. Okay, good. So again, guys, like I said, this is the line, right? Again, random forest has two, right? You can do both classification and regressions. So we are doing a classifier here. Anything else I should highlight here, Silius? I think looks good, pretty good, yeah.
To be honest, I had an extra version that I did manage to make this as a bar chart.
Okay.
In ascending order. But I said no, leave it.
The feature importance, right?
But
yeah,
but
very
this
good,
is not big importance because I can read the data and understand from my text what's going on.
Yeah, very good. Yeah, this is good. So again, once you have the feature important, then it's just a matter of putting into a data frame or something. You can sort and right, you can graph it. Yeah, exactly. But it's pretty I'm just looking at this, right? I can say it's pretty, pretty interesting, right? Yeah. Huh. All right. So like the highest one's age, location. Yeah, right. These I can understand. Yeah, these could be very important, right? Yeah. So good, very good. I like this data set, and it's timely. I know it's kind of a little depressing, but but it's a real world data, right? So, no, cool. I like the tree consider. Okay, very cool. Good. Very good. So that's random forest, right? Anybody did the regressions? Any regression on random forest? I'm curious. So I can quickly highlight. I'm just randomly. Maybe Richard. I just see your notebook. Let me see if I can bring it up. Again, guys, like I said, there's no need to be even if it's not complete, right? Like I said, I'm looking for examples, right? So, all right, good. There we go. Right. So here, basically, we are doing a just synthetic data. Just make regression, right? Again, you can sort of plot this to see, basically X and Y, right? Imagine you're trying to predict X and Y. And again, when you do make regression, it gives you random data. But the beauty is it already gives you X and Y, right? So you're pretty much set at that point. That's why I want you guys to start with this, because as you can see, real world data, you need to do a lot of manipulation and feature engineering to bring it to a format you can do X and Y. Okay, X and Y, right? There we go, split. And then that's it. Random forest regressor. See the difference? Regressor, right? Not classifier, regressor, right? And that's it. Once you have this, just fit and train all the while. And then also, here's a parameter, right? Parameters, and that feature. There we go. Here's a feature importance, right? So you can see, remember it's just two variable, F1 and F2, two-dimensional variable, right? So it just seems like feature one seems to have a little bit more importance than feature two. Remember, these two, they should add up to 100, right? I was in one. Yeah. Good. Very good. That looks good. And remember, in regression, so here's the thing, right? In regression, you got to do different metrics, right? So this is another thing you got to understand. Right, when you guys do cross-validation here for classification, you could be measuring things like accuracy, or pretty much anything from the confusion matrix, right? Accuracy, ROC, AUC, right? You can tell what to measure, and if you don't say anything, it's by the default is accuracy, right? But for regressions, we have a different metrics, right? We have R squared, right? MSCs. Remember, you have to always think like, what's my error metric, right? Because I've seen like people try to use accuracy for regression. That's not correct, right? Because in regression, we don't have such a case like there's no accurate, right? Because remember, the only thing you can measure is like how close you are to the actual value. So those are measured by mean square error and R squared, right? So anyway, so again, all these should be pretty familiar to you guys. And one of the things I am showcasing the notebooks, and let's say you're sort of struggling, with one second, and you're looking at some sample code. Please don't copy paste, right? Type it on your own. Even though you can look at the answer, right? That's fine, but type it on your own. Trust me, it really makes a difference, right? Because sometimes I copy paste code and I'm like, okay, yeah, that seems to work, and I move on, right? But when I start typing, that's when like these little nuances, right? For example, is it like a square bracket or a curly bracket? You know what I mean? Like it's little things that you have to think about when you're typing your code. That's when you learn, right? Anyway, so yeah, so take a look at the solution, right? There's nothing wrong with that, but please type it into your own notebook. Right? Very good, very good. What is this one? Bike sharing data, right? So I'm curious, was the bike sharing, I know it's a kind of a tough data to get right. How are you doing here? X describe, okay, X and Y. Okay. Okay, interesting. Okay. That's nice. I really love this. Okay, yeah. So feature important, right? So it's pretty cool. So you can sort of see here, right? Temperature plays a big role when people are renting bikes. Yeah, interesting. Yeah. And year also. Okay, I think okay, that's interesting. Yeah, and season somewhat. I'm not sure what the A temp is. What's the A temp? Is it human? Okay, no, actually, yeah. So anyway, so some version of temperature, right? That's pretty good. So anyway, so when you do feature important, it's pretty amazing to see, right, what you get. That's pretty good. And also, another thing I want to make sure you guys have done this is, right, end jobs. Has anybody looked at what this is? I mean, typically, if you have small data, the training will be pretty quick. But if you have some sizable data, your training is going to take some time. Now, so random forest, as you guys know, right? By default, you're training what? So if you take the default attributes, you're training 100 trees underneath. And this takes time, right? You're training 100 trees, so it takes training time. So by specifying end jobs, right? And this is something part of scikit, right? All right. So some of the documentation is not okay. Right. So what end jobs is going to do, right? How many jobs to run on your machine? And especially into random forest classifiers, right? That's important because the random forest, right? You're actually going to, right? Parallel, because you can train this data in parallel. So let's say you have a machine that has 4 CPU cores, and these is pretty common, right? Even when you buy a laptop, you at least have 2 to 4 CPU cores. So what you can do is you can run your job in parallel. Because when the random forest does, remember, you guys know how the random forest works, right? Once a split is done, training individual tree is independent. There's no dependencies, right? So anyway, so right, so you can give it a number. Say, let's say you have 4 CPU cores. You can say, we'll use 4, right? Or basically you can do -1. What is -1? Meaning use everything. Yeah. So that's like so depending on number of cores, you can. So again, let's say your training takes let's say I'm just making this up. Your training takes 30 seconds. Just play with this parameter. Just give it -1. Right? So use all the CPU cores, and then see, and that should really cut down the training time. And this matters, right? Because when you're doing large data sets, easily like tens of megabytes, anything bigger than that, you definitely want to use that. Cool. Very good. Yeah. Very good notebook, Richard. I like that. I really like the feature importance. That's very good. So again, right. So and these are some of the things again. So I want to highlight. Right. For example, you guys already know how to do all this, right? It's like you guys know how to do graphs and everything. It's just like kind of putting everything together, right? And that's a skill sort of you will develop as you sort of do more and more notebooks and more exercises. Kind of this presenting your results, right? So yeah, so kind of so and that's why we sort of spend some time early on, kind of doing the basic graphs and things like this, because I want you guys to think about, okay, here's my result. How can I best present it? Yeah, very good. Cool. Good, guys. Very good, very good. So R squared, that's good. Okay, that's a pretty good R squared. Okay. And test. Okay, test. That's a good test R score. Yes, okay. Yeah, that's pretty decent, because the Austin data set is a little challenging, right? Yeah, so you can do some basic data manipulation to yeah, but this is pretty good. Anything else, Richard, I should mention, I should highlight here? Looks pretty good as it is. Yeah. Again, yeah, very good. So look at the score. Cross validation. There we go, right? There we go. That's the cross validation. Yeah, perfect. So again, same thing, right? Now you're getting the hang of this. So once you sort of find an algorithm, then cross validate always, right? So you can, okay, so let's see, test R square. Interesting. Okay. Yeah. So average test. Okay. So definitely is overfitting here, right? I can see here. So yeah, and this is the thing, right? I mean, yeah, this data set is a little hard to get right, because there's a lot of hidden attributes. So this is something you can use as a challenge. Like, for example, let me go up here, right? Right. For example, people have, there are a lot of notebooks to kind of, understand this. If you do a search, you'll find some notebooks. Kind of look at and see how people are, how people are doing feature engineering, right? For example, so I know there's like a timestamp column, right? And you can say, what time is it? Is it like early morning, like afternoon, right? So what you had to do is you had to basically split the timestamp into actual, right? Like an hour of the day, something like this, right? Anyway, so you can sort of see, do some search. But yeah, this is a little challenging data set to predict. Anywho, but this is good. So I always say it's a process. That's important, right? Like, you guys know, okay, hey, I know how to manipulate data, I know how to tweak this, right? So once you guys learn this, you can pretty much tackle any data set. Very good notebook, Richard. Anything else I should highlight, Richard? Yeah.
No, I think that's pretty much it.
No, that's very good. That's very good. Yeah, yeah. All right, guys. So basic workflow, right? So now we are kind of, so I'm always kind of asking you to say basic, right? Basic algorithm. Just start with synthetic data, right? Because the idea here is just to kind of get you guys quickly to use the algorithms. And synthetic data, when you do synthetic data, you get X and Y right away, right? It's, everything is taken care of for you guys. Once you're comfortable, then you take a small data, real world data, and then say, okay, now let me do random forest. And most of the time, what are you going to spending time on? You're going to be spending time on shaping the data, right? And once you get more comfortable, right? So that's how you sort of build up your confidence level. All right, guys, very good notebooks. So I put the links on the, right, I'll put this here. All right, give me one moment. Put the highlight. And also, yeah. Good, guys. So, right. So this way you can take a look at these two. Again, thank you, both of you guys. Really, really good work. I appreciate this. Yeah.
A question.
Yeah,
now my mind is not going away from this thought I have. Tokenizing text. Is there anything is there any easy way, or I have to go through loops and do it myself?
Text tokenizers, you can do. There are a lot of libraries that will do for you. NLTK is what I would recommend, right? So can I now I'll ask you guys, right? Text tokenizing, NLTK, right?
Yeah.
Yep.
To utilize it, say with one of the pandas feature.
Exactly. Yeah. So basically, you can use NLTK or Spacey. These days, a lot of people are using Spacey more, right? Because Spacey is a kind of a little modern toolkit. We haven't done much text. Did we do text in spam data set, right? When Naybase? I'm kind of curious. Yeah.
I think we did something.
Yeah. So, right. So, but that's probably already been a your data's pre-split for you guys, right? So let me see, Naybase. Let me see how it split. Okay, because because it's part of the pipeline anyway. Yeah, exactly. Yeah. So here's not very explicit. Yes. But yeah, I like the question. Question is basically how do you tokenize text? Basically, there are a lot of algorithms. So NLTK is a pretty old. It stands for Natural Language Toolkit, right? It's old. It's a classic. It's really well tested, but you can use that because tokenizing text is pretty straightforward, right? It just breaks down into words, and also Spacey is another one we recommend, right? Yeah, and then once you have text tokenized, then you can sort of do like things like count vectorizer, all right, or word vectorizer, word to vec. Because remember, once you tokenize words, you have to somehow turn the words into vectors, right? These are some of the simple ones, right? Count vectorizer word to vec, right?
I tried to do it manually. The problem I had there, the actual text, it was actually a log file of a web server. The log file itself was, say, 100 kilobytes. After trying to, to make them categorical things, every word to have a specific ID.
Yep.
It became something like 400 kilobytes
yeah,
to
the
store
dimension.
And I don't know if it is actually to save time or to waste memory.
Yeah, because because you can imagine when you break it into words, right? Each word becomes its own vector, right? Exactly. So you have a very sparse column. Yes, your number of dimensions is going to go up, right? But once you, and that's why these guys are good. Count vectorizer, word to vec, right? They will encode them in a very compact format. So it's okay to kind of, just, go with this, right? So what you're going to have is something like this, right? Let me just scratch, put like a scratch, like for example, like a line of word, right? So let's say one of the things like, let's say you have some text like, right? So let's say these are all like one word. What that's going to become is like, now it's going to become like this, right? A, comma, B, comma, C, right? Comma, D, right? And then what word vectors do is like, they will sort of take this into like some sort of number. They will say, this is like a, something, right? They'll sort of convert it to a vector. So your first task is, taking this string, right? Let's say this whole string, right? Into, you're breaking them into words. And that's where NLTK and all these guys are going to help you. The next step is basically, right, taking these word columns and turning them into vector column. So I wouldn't do one-hot encoding. See, right? And that's why text we had to approach a little differently, because one-hot encoding, it'll basically turn each word into column, right? So it's much more efficient to do something like a word to vec encoding to turn them into vectors, right? So anyway, so do some reading on these, and and then you'll see how they are being used. So basically, steps is break them into words, and then don't do one-hot encoding, just turn them into vectors. And this will be a much more compact notation. Does that make sense?
Yeah.
Because if you try to one-hot encode, like especially log files, you'll end up with lots of dimensions, right? So that's why text we had to approach a little differently. Yeah, good question. Anyway, so yeah, try a few things out, and then if you have any questions, we can definitely discuss it. Yeah, yeah. Very good, guys. So we looked at the notebooks. Any questions so far? So why did you run, cross-validation for random forest, right? Because remember, even in random forest, doesn't matter which algorithm, when you do train test split, at that point right there, you're picking a data set, right? And what cross-validation does is like, it's how do you say it, goes through systematically through all your train and test, data sets. Exactly. So because otherwise, I forgot, it's like because it's random state. There we go, right? So when you set a random state, right, it's basically the split point. And when you do cross-validation, so here's the thing, right? If you're going to do cross-validation, you don't need this step. Because why? Cross-validation will do this for you automatically, right? So here, so when you do cross-validation, right, you just want to give it a whole, X and Y. Actually, here I want to think about, you want to say cross-validation, you want to think about doing the X and Y, not X train, Y train. So double check this one for me. Let's use, right? You want to give the full X and Y, right? So because cross-validation internally will do this for you. Yeah. Good question. Good, guys. So where are we in the overall scheme of things? We are decision trees. So we look at our algorithm map, right? So we are done with supervised algorithms. So kind of a little review, right? So we started with regressions. Remember, just a simple linear regression, right? And then we generated classification. We did quite a few classifiers, right? So simple logistic, SVM, naive-Bayes. I think we did a KNN also, right? And then we went to decision trees last couple of weeks. Now, decision trees can do both regression and classification. And you guys did one each, right? So decision trees, we did 3 trees: decision trees, random forest, and XBoost. By the way, sorry, I didn't go through an XBoost, a boost tree algorithm, but you will see it's very similar, right? It's just basically one line. You had to basically substitute to initialize the boost tree, right? Just like you're doing random forest here, you will see you'll see boost classifier, right? So behave the same way because they underneath they use the same decision trees. Okay, is that gonna make sense, guys? Right? So we covered 3 tree algorithms. So if you look at the competitions, a lot of the competition you will see people end up using random forest or boost trees because they perform really well, right? So and also the reason boost trees work really well is because they can like remember random forest and boost trees, they are like ensemble. When it's an ensemble, what they do is they create many small trees and then aggregate their results, right? By doing so, they can they alleviate some of the problems we experienced before. Like for example, so we call decision trees as weak learners, as in they're okay, but they don't give you really good results. But what random forest and boost trees do is they take the weak learners and then they keep adding, right? So multiple weak learners added together can perform better than one weak learner, right? So that's the theory behind these guys. Again, so I updated the reading material for you guys. Right? You can look at the random forest and boost tree reading, right? So there are some good blogs that explain how the boost trees work. Right? So kind of read up on that, but you guys know how to use them already. So if you look at the competitions like Kaggle competition, whatever, you will see a lot of the time people using boost trees and random forest because they give you pretty good results without doing a lot of work, right? So that kind of makes so that kind of sums up supervised. We'll come back and revisit supervised later in labs, but I'm going to sort of wrap up the theory here. Any questions on this one, guys? Supervised learning. Very good. Okay. So also, time-wise, right? Because I know next week is Thanksgiving in US, right? So what I like to do is kind of you guys can tell me how you want to approach this. I want to we can make next week as a break week if you guys like, or we can continue going. Right? We can make next Saturday. So you guys can tell me what your idea is. Maybe not right now. We can do it in the chat, in the Slack if you like. I like to kind of keep going because Thanksgiving is Thursday, right? And then so I hope we can, because the reason is I want to wrap this up, right, before the end of the year, if possible. Again, it's up to you guys, right? But if you want to go a couple of weeks in January, that's okay too, right? So the way I want to sort of run this is quickly run through the algorithms. So we've done through all the supervised algorithms. And I want to cover a couple of algorithms from unsupervised, k-means, PCA, and also recommendations. So that's 3, right? Once done this, maybe the last couple of weeks, we will do some projects, right? So do some real world data, right? Maybe group into teams, things like that, right? So that's my idea. So if you go a little bit into January, that's okay. But I want to make sure. So right now we are showing you guys algorithms, but towards the end, we're just going to give you a problem and say, okay, here's a data set. Choose the best algorithm that works for you guys. Yeah. So, all right. So let me look at unsupervised real quick. Any questions, guys? Before we, any questions or comments? How we want to do this? Okay. So let me cover some unsupervised slides. You already have the slides already, right? So I'll go through this one real quick. So we are on supervised learning all, in the last few weeks. So what is supervised? Basically, we train, right? And then we make predictions. So training, we do training data, and prediction, we do prediction data, right? So again, we went through a lot of the best practices. How do we do train test split? And then how do we stabilize the training testing like by specifying a random number, right? And then we sort of advance a little bit to the next level and say, okay, now we are going to do cross validation to do our train test split, right? All that. In unsupervised learning, what you will find is there's no training. We give the entire data to the model and ask the model to make predict some patterns. Right? Very different approach. So a lot of the time, when you get data, when we did our supervised learning, we always things like label data, right? So what is the label data meaning, right? For example, let's say you guys are training on, for example, COVID prediction, right? You already have a data set that has sample data. If these are the inputs, the output is yes or no, right? And that's what the algorithm is training on, and this is what called label data. But what if you don't have label data? Right? What if you don't have like a sort of something for binary classification, but you still have data, but you're not trying to predict like a yes or no, or like a regression. So that's where you want to consider unsupervised, because these algorithms, they're very good at clustering data, right? Meaning like trying to find patterns. So let me show you some of the examples, right? I'm going to make sure we understand data. Right, for example, when you do DNA analytics, we want to find out who has similar DNA. So you're not trying to predict, right? You're not trying to predict, so you're trying to find patterns. So I'm saying, whose DNAs are most aligned, right? So things like that. Online shopping, we talked about this quite a bit, right? When customers buy things, right? You're not trying to predict if the customer is going to buy this or not. That's another problem. What you're trying to predict is basically who are the customers who kind of fall in the same group. For example, let's say, could be new parents, right? If you're a new parent, you tend to buy a lot of baby stuff, right? Things like diapers and formula milk and all that, right? So that kind of puts you into one group. Let's say you are let's say you are into gardening. Then you sort of end up buying a lot of garden-related stuff, right? Or let's say you are somebody who do how do you say house projects, like home projects, right? So you're making you're buying a lot of home project stuff. Right? So anyway, so what we're trying to do here is trying to find which group you fit into, so we can give you like promotions and things like this, right? So that's why, right? So very different distinction. We're not trying to predict, but we're trying to group. Okay. So let's look at one use case, which is clustering. Remember, clustering is part of the unsupervised algorithm, right? We're trying to find group data together. And here we're going to look at k-means algorithm. Okay. So again, where are we? Unsupervised. We are looking at clustering, right? And we're going to look at k-means algorithm. Okay. So the way I start the clustering is, imagine this data, right? I give you some data. Let's say there's 2-dimensional, right? I have x and y axis, right? And if I show you the data and say, do you guys see any patterns in the data? You say, sure. I see 3 groups. Now, I don't know what these 3 groups are, right? But I do see 3 groups. Because remember, then, knowing these 3 groups, that's actually classification, right? Think about it, right? You guys have already done this already, right? So when you do a classification, let's say, for example, I'm grouping alcoholic drinks, right? So you're classifying them as, oh, this is the white wine, this is the beer, this is the red wine. That's classification. So let's say, I gave you some basic data about drinks, right? I don't know, like alcohol content, clarity, things like this. And based on the input, you have to basically, categorize them as like red wine, white wine, or beer. That's classification. So that we have done. What if I don't have the data? What if I don't have that column that says, right? Remember, imagine a column, right? Imagine our input columns, right? Kind of like this, a bunch of inputs, right? And then finally, we have that one column that says, whether it's like white wine, right, red wine, or beer. Let's say this column doesn't exist, right? Meaning, this is the label, right? I don't have the label. How do we find patterns? So that's where, clustering comes in, because, you can sort of, here I'm just doing as a plot, right? You can graph the results and say, oh yeah, I see kind of, 3 distinct groups. I don't know what these are yet, right? That's the next step, but at least for now, right, we are able to segment these into groups. Is that going to make sense, guys? Right? Sometimes people get confused between clustering and classification, right? So classification is when you actually have label data. When I say label, this is a label, right? You're trying to predict what the label is: red wine, white wine, beer. But if you don't have labels, you can still segment the data or group the data, but you just don't know what the groups stand for. So we just say X, Y, Z. Yeah.
As I understand, the clustering is going to give you, say, one feature with different, say, classes. Is it something that we can simulate somehow in our brain with the supervised learning? Imagine you have one feature that can have different values, and based on the values, you can cluster them on every value. Yeah?
You could, yeah. So you could technically, right? So what you can do is so the way I sort of look at this, let me paraphrase a little differently, right? Let's say you have unlabeled data and you come up with some sort of a clustering, right? Using one or more attributes. Then you can use that for training, right? So kind of the way you're thinking about this is like, let's say you have, let's say this label is missing, right? So first you do unsupervised, right? And then create some, create like let's say groups or whatever, right? And then here, then you can do supervised, because now you sort of you're done some guessing of the clusters, and then you can treat these as labels and then do supervised learning. I think that's what you're.
So the set of the clusters could be named the feature, and then the specific clusters could be named specific values of the feature.
Exactly, right? So, so in this case, right? Let's say in this case, right? Let's say I don't know what these are, right? So I'm naming them X, Y, and Z. These are my features, right? Then I could kind of, do some supervised algorithm, and these are my labels now, X, Y, and Z, and then I can do training and prediction, right? Now this whole thing is called semi-supervised. You guys probably remember this from very early, right? It's called semi-supervised because why? Because you are kind of right. You're kind of guessing the labels first. Why? Using clustering. You remember, like these are not like real labels, right? These are labels we are guessing. And then using these labels that we guessed, you do supervised learning. That's why it's semi-supervised, because it's kind of in between. Make sense, guys? Yeah. So yeah. So a lot of the time, supervised learning is like a first step of machine learning. Like you get unlabeled data. Like for example, one of the examples I noticed is, I'll give you an example. Like somebody was analyzing machine log files. So in the machine log files, they would just get like error or something, right? So what they first did was they kind of started classifying what kind of messages are we getting, right? And then they cluster some messages together. And then a human will go look, read the message and say, okay, these messages seem like an error, right? These messages seem like a warning. Right? You know what I mean? Like you guys get the idea, right? So somebody actually go and manually kind of reads the message and sort of now they're classifying it, and now they're finding patterns, right? So yeah, so you can sort of mix and match a little bit of unsupervised and supervised, and then with some human or human oversight. Yeah, good question. So these are some of the things we will do. I want to get to when we do our final projects, right? Sort of combining these things, and then kind of sort of do like an end-to-end project. Yeah, good. So that kind of makes sense, guys. Difference between clustering and classification. No? Okay. So, and here's another use case. Anomaly detection, for example. Let's say I'm analyzing network traffic or like log files. Let's say most of the logs are in this area, but when I started seeing logs on this area, these are different, meaning we haven't seen them before. Now again, remember, the clustering algorithm only says, hey, these are different. I see a different group. Whether this group is like, for example, let's say you're analyzing web traffic. I'm sorry, network traffic. Let's say this is like usually web traffic, right? And then somebody tries to, I don't know, uploading a large file to like a Dropbox or something, right? So what that is, it'll say, hey, you know what? It's something different. It doesn't mean it's like somebody hacked into the network. You know what I mean? That's for you to go figure out. But the algorithm will highlight is like, I'm seeing, let's say my usual website traffic is here, and then I see like another traffic. I don't know what this is. I just know it's different. Then we can go investigate and say, is it like somebody hacking in, somebody uploading a large file or something, right? Whatever. So, good guys. Google News, you guys have seen this earlier, right? What they do is Google News is like, right, when you go to Google News, right, let me show this right now. Right, so usually like a big, right, big like a news story, right, and then all the sub stories. So what they do is they go read each story, and they figure out, okay, what subject are they talking about, and they group all the stories together. Right, so for example, right, so this is a story, they give you like a first, and then if you look at the view full coverage, then they will, they will kind of, give you all the stories that are related to the same, right, same, right, same subject. Right? So include tweets, news, and all this stuff, right? So anyway, so that's pretty cool. So you can pretty much look at, right, anything, right? So they're like a basic news story, and then and there are a lot of coverage for a news story, right? And then if you click at the full coverage, what they will do, right, is basically all the stories talking about the subject. So clustering, right? What we are doing is we are clustering similar stories together. So obviously our clustering is lot of dimension, right? Now I have like hundreds or even thousands of news stories I have to cluster, right? But yeah, that's what Google News does, and it's pretty good. Right? Okay. And and this is one of the labs we will do, is clustering Uber traffic data, right? Uber pickup data. So you can actually predict when you cluster the Uber traffic, right, you can predict where the demands are. So, okay. Question, guys? All right. Sorry. All right, guys. Sorry. All right. So we looked at cluster use cases. Have you talked about this earlier? Probably, right when you go shopping, this is called product placement, right? So what they do is, right, next time you go shopping, take a look at this. They will actually, when you walk down an aisle, they will have those islands. They're called bins, right? Island setup, and they will have some items. And they look at the aisle where they are in. Sometimes they have no relation. So they seem like some randomly placed items, right? But they're not random. They are very well examined, because 1 second, guys. Sorry. Okay, yeah, go on. Right. So what they do is they look at people's purchase patterns, and then figure out what items people are buying together. So this looks like a milk aisle or something, right? So let's say you're walking down the milk aisle, right? And if they realize people who buy milk also buy, say, cereal, right? So they're gonna put some cereal bins, cereal boxes in the middle, right? So even though you just went to buy milk, you'll say, oh yeah, I'm running low on cereal, so might as well buy it, right? Because imagine if it's not there, you wouldn't have gone to the cereal aisle, right? You just get your milk and get out. But since it's right there, and milk and cereal, this is just an example. But it's like an impulse buy, right? So next time you go shopping, when you see this island set up in the middle, kind of look around and see why they did this. And because I just think these are like random placements, but there's a method to this, right? I mean, they actually figure out which items to do, put on these islands based on purchase patterns. And Walmart did publish their item category, right? So they looked at their people's purchase pattern, and they came and say, oh, these are the sort of categories we see, right? So things like just came to buy, like, let's say it's cold season starting, just came to buy some cold medicine, right? Or you just came to buy some grocery, or you just try to make milk, right? So different things, right? So anyway, so why does it matter? Because once they understand how people purchase, they can put things together, right? They can do promotions, things like this, right? So all right, guys. So what we are going to look at, we're going to look at how do we do clustering? We understand the use case for clustering. How do we do clustering? One of the popular algorithms, k-means. So we're going to look at that. So let me look at k-means real quick. And this is the exercise we will do this week, right? K-means. So again, where are we? Unsupervised. We're doing clustering, and we are doing k-means, right? So let me show you guys the k-means in a visual way. It's very easy to understand. So look at the data set, right? I showed you 3 data sets, but if you ignore the color coding, it's exactly the same data set, right? So right, to take a look at this, just imagine they're all the same color, the same data set. So now the task is, I'm telling you guys to say, okay, go find me, let's say this is my data set. I say, go find me 2 clusters or 2 groups. So k-means goes and finds 2 groups, and right, you can sort of see here, right? The color coding now indicates a group. So there's a blue group and let's say yellow group, right? Same data, I ask k-means to go find 3 groups, ck equal 3, right? So now k-means comes back with 3 grouping. Again, we color coded them just easy, as we can easily see them. You see, right? Green, blue, and yellow, right? Same data, say go find me 4 groups, finds 4 groups. Now, question for you guys. Which of these groups you would think makes sense? As in, like, when you visually inspect the data, would you say 2, 3, 4 groups? How many groups would you guys pick? What do you guys think? 3? Yep. Yep.
Looks like
3 groups, maybe 2 groups, right? Because 2 looks okay too, right? And this is the deal, right? Because there's no precise answer. So some of you pick 2, some of you pick 3, and both of them could be correct. And this is one of the things in unsupervised. Sometimes the answer is a little fuzzy.
May I ask here?
Sure, go on.
Is there any metric to actually compare different sizes of cluster solutions?
Yep. So there are some metrics I'm going to show you guys, right? Even the metrics, they don't give you an accurate answer. We'll say, I'll show you guys, right? Like, for example, in the super, like, for example, you guys did random forest, right? If I ask you, what's your accuracy? You can give me an answer. You'll say, yeah, I'm like 60% accurate. There's a number, right? But in unsupervised, sometimes, these things are a little, right? A little fuzzy. Let me show you an example. So how does k-means work, right? The basic idea is very simple. So let's say these gray points are my data, right? The gray squares, right? Those are my actual data. Then I ask k-means to go and find, say, 3 groups. So what it does, it randomly places 3 center points randomly, right? Doesn't need to be in the center. So the red, blue, and green, these are center points. Then what it does is it sort of starts grouping this item closest to each other together. So red closest here, green here, blue here. Right? So that's the initial grouping. Then what it does, it sort of calculates the distance between the points and the centers. And then it moves the centers around. You can sort of see how the red center was here, and then now it's moved to here. Yeah, go on.
You know what I could think on this thing?
Sorry, one more time, please. What is it? Sorry, was that?
Can you
Yes.
hear me?
Yes, go ahead,
You
please.
know what I would think? If you go, say, back to the previous, messed
This
up.
one? Yep.
Yes. What I could think to measure the somehow accuracy or lack of, I could say, in different numbers of clusters. Imagine I have the clusters now, say not 2 clusters or 4 clusters. Let's get the 4 clusters over there. I could imagine that I could use the cluster center and the cluster radius.
Yep.
From the whatever center point to the most far away part of the cluster.
That's right. Yeah. So you see 3 plus, right?
And then I could measure how many misclassified points of other clusters are actually within that circle.
Yep. Exactly. Yep. Yeah, and that's a metric they use,
geometrically right? Thinking.
That's right. So here, exactly, you're right. So that's a metric they use. It's actually called, it's basically a distance, right? And that's what you see here, right? So what they do is they measure the distance between them and the center. But what k-means does is, if the center is too far off, it actually moves the center, right, to closer to the data. So you can see, that's what you see the red one, right? It used to be here, but it moves it here, so you can actually do better grouping. So once the centers move, then it regroups again. See, I have red, blue, and green, right? Compare these two guys. This is a better grouping, right? Because now I can sort of see, because here it was like, green got most of the stuff, red only had one. But now in this grouping, now the red center has moved, right, to accommodate, and so now it has more data. Now the data is more evenly divided, right? So this is what k-means does. It'll sort of keep moving the centers around until it has a good good grouping. So let me show you a an animation. Let me see if this is still online. The standard one. Okay. There you go, right? So take a look at this one. So this is a pretty good, right? So this is like a, again, the link is here in the I'm using this Stanford link, right? You can play around with this if you like. Now, so here are my data. The black points are my data, and I say find three clusters, right? So it randomly put 3 triangles. See, red, not red, orange, green, and blue, right? Now, when I click on this button, it's going to keep iterating. It's going to go through the data, like every click, it looks at the data one time. And keep an eye on these triangles and see how they move, okay? See how the centers are moving, right? And if we keep clicking, you see, right? They'll eventually go find the grouping. Let me do one more. Let me do refresh. I'll get another random. So here we go. Here another random data. So here, I have random points, random center points. So let me see. Every time I click, you will see, right? See how they're moving, right? So after a while, you will see the cluster will stabilize. The center points are moved, and that's pretty much it, right? So now the movements are pretty small, right? So it kind of found 3 clusters, right? 1 cluster, 2 cluster, 3 cluster, right? So maybe you say, what? Maybe I want to do 4 clusters, right? So I say, right, there we go. See, you get the idea, right? So as we kind of keep through, right? Anyway, you guys get the idea, right? So every iteration, the grouping gets more and more refined. So how do they do this? Very simple. What they do is they measure the distance, right? They measure the distance between the center point and the actual data points. And remember, you cannot move data. Your data is fixed. Only thing you can move, you can only move the center points, right? Because center points are randomly placed by us. Does that make sense, guys? Kind of visually, right? Do we understand? Yeah. Right. So we can look at this too. So that's why you sort of see, right? See, right? See how they're kind of moving and finding their own clusters. And you might say, here, my blues are a little, right? You can see, like I said, you'll say maybe this should be part of orange. So if you kind of keep iterating, see how they become orange, right? See, so the clusters will get more and more refined. Cool. So does that make sense? So this is why we love K-means, because it's very simple. It's very fast, because all you're doing is you're basically calculating the distance. It's basically your Euclidean geometry, right? Distance between the center point and the data point, and move centers around. So you do a few iterations, and after that, we will say the cluster is stabilized. Yeah. Any question on this one, guys? Does that make sense?
So I think it takes the skewness of every cluster or to understand where to move the next point.
Yeah. So basically what they do, so what they do is, so remember our sum of squared errors, SSE, right? They use a variation of that to calculate the distance, right? So the idea here is, right, you kind of want to you want to find a center, right? This is Stanford one. You want to kind of find the center, but you don't want the center to be too far away from the data points, because then the distances will be pretty large, right? So what they do is they measure the distance between the center and the points, and that's your sum of squared errors. Remember our sum of squared errors, basically, right? Just like we did in a regression, we're calculating a distance. But what you want to do is you want to calculate all the sum of squared errors across all the all the clusters, and then make sure they are they are minimal point. You don't want one center to be randomly away while the others are pretty close to your data points. So you want to take care of all the clusters. So, and this is basically what is it called? Within WSS, I call it WSSE, right? So right, within some distance, and that's what they try to minimize. Because remember, every machine learning algorithm, you're trying to minimize an error, and here the error is the collective distance in all the groups, right? So, right. So within cluster, sum of square errors, right? Remember, so we know sum of squares, right? And it's basically within cluster, meaning each clusters. Yeah. called WSSE, right? That's the metrics they use. So let me show you an example, right? Let me work with an example, and then and this we will do as this week's exercise. So let's say I have some cars data set. So here's the car names and the car attributes. I want to group these cars by just an MPG and cylinder. So first I'm doing K2, right? I say, okay, you know what? Go find me 2 groups. By the way, I have how many? 32 data points altogether, right? It's just a very small data set. So I say, okay, find me 2 groups. So K-means goes and finds groups and basically comes back with, okay, so this is group 0, right? And then group 1, 2 groups, right? 16 cars each. Look at this group first. So remember, we are grouping by 2 columns, miles per gallon and number of cylinders. So here, usually like low mileage cars, 10, 13, 15, right? So basically 10 to 19. And 8-cylinder and 6-cylinder cars. And here, the next group, high mileage, like 20 plus to 30, right? Like low 30s. And their cylinders are mostly 4-cylinder and 6-cylinder. So you can already see, right? I like 2 groups kind of forming. So the way, I'll look at this like, I'll do like this, right? So imagine I'm doing 2 groups, right? Kind of like, imagine like this, right? Our kind of a, Legos example, right? So I have 2 groups. So, and then the group, when you look at this, they kind of look similar. They are low mileage. These are low mileage, big engines. These are kind of high mileage, smaller engine cars. And when I calculate the WSSE, it's 425. So for 2 groups, K equal to, this is the formula I just mentioned, right? The WSSE formula, right? You calculate the error. It's basically 425. Okay, got it. So now the same car data, I'm telling K-means to go find me 4 groups, right? So split them into 4 groups, right? So instead of 2, split them into 4 groups. So I end up with 4 groups here, you can see, right? So remember, groups are named 0, 1, 2, 3, right? So this group, I only have 2 cars. So that's another thing in K-means, right? You don't have to have the same number of data points in the groups. So look at the 2 cars, right? These are like very low mileage, only 10 mpgs, really large engines, right? So they are pretty similar. All right. Let's look at next group. These are kind of, 15 plus or minus is miles per gallon, but also, most of them are 8-cylinder cars. So as you can see, these groups are now much more uniform, right? Compared to the 2 groups we had earlier, it was a little mixed, right? But these 4 groups seem pretty well sorted out. Okay. Let's look at this guys, right? Group 3, 6 cars out of 32, kind of a high mileage for us, right? 20, high 20s and low 30s, right around there, and mostly 4-cylinder cars. And this group is a little bit of a mix, right? This is kind of, maybe high teens, around like 20 plus or minus around their mileage. But cylinders are kind of mixed, right? I have 6-cylinder, 8-cylinder, and 4-cylinder cars. So this group, maybe you can do some more refinement. But the other 3 groups, if you look at this, they look pretty good, right? They look very similar to each other. Do you guys see that? Huh? So now if I calculate the error, the same WSSE metric, it's 130. So you can see the error has come down, right? From K equal 2, it was 425. Then K equal 4 is 130. So error has come down quite a bit. So let's say I cannot keep going. Like, so I cannot keep doing, right? I keep increasing my K, right? 2, 4, 6, kind of like more and more clusters, and I plot the error. So it kind of looks like this, right? So here, x-axis, we have K, right? Starting with 2, right? We have 425. And then we did 4, which had 125 or something, right? So I can keep plotting like this. So my errors keep going down. That's good news, right? When K is approaching 32, my error is pretty much 0. Anyone have a guess why error 0? Like when I'm approaching 32, I'm achieving 0 errors. That's good, right? 0 error meaning that's good. Any guesses? Why when I'm approaching 32, my error is kind of declining? Yep.
more clusters than cars.
Right. Remember, so what's it's doing is, remember, I have 32 data points. Remember this? Right. My overall data, I only have 32 data points. Right. So what exactly? So what you guys are having is, I see the chat window here. Yeah, very good. Yeah, exactly. So remember, I have 32 cars to group. When I group 32 groups, what's happening? Each car is its own cluster. Right. I mean, that's why my error is 0, right? Because each data point is its own cluster. So error is 0. That's perfect clustering. But it's not very practical. It's technically accurate, yes, right? Each car has its own cluster, but it's not very practically useful. And so imagine you have 1 million customers, and then you go tell your boss, I found 1 million clusters, right? You probably are not going to get a bonus for that. You see what I'm saying? So technically correct, yes, each car has its own cluster, right? But not practically useful. So what is the right number of clusters? Right, and this is where the sort of the fuzziness comes in, right? So if we ask you guys to say, okay, here's my error coming down, and you can see, right? And this is true in K means it's going to come down very sharply initially, and then kind of taper off. So usually what we do is we pick the ideal number of K somewhere in the elbow region, where the error is kind of tapering off, right? So if I ask you, okay, what would be an optimal K? You might say, someone might say 5, someone might say 6, someone say 8. And like there's no disputing that, right? So that's why the answer is always like a range, not like a one number. Does that make sense, guys? Right? In K-means. So we do have an error metric, right? But thing is, the error metric is basically, it's just an indication. So usually we pick a optimal value for K somewhere when the K is kind of starting to, the error is starting to taper off. Does that make sense? So in the Walmart example, remember, do I have this one? Yeah, let me go back to the Walmart example. Remember they were doing the trip clustering, the shopping clustering. There was that. Yeah, right? So in Walmart, I think they came up with 35 or so groups, right? So their K, like, how many clusters? 35. Again, it could be 35, something like that. Don't quote me on this one, something 30, right? So let's say 35. And if you ask me, why did they do 35? Why didn't they do 32 or 40? Right? So what they've done is once they've done the initial grouping, they went back and looked at the grouping, the group data. And and this requires some inspection, right, of the actual data management. And they say, oh, what, this grouping sounds about right. Meaning, when people are trying to do grocery, right, the grocery baskets are mostly grocery items, right? If you further subdivide them, then right, then you get just too granular. But if you sort of instead of 35, you came like only 20 groups, now you have a bunch of mixed merchandise, right? So for Walmart, for their data, the 30 or like 35, I think, right, was the sweet spot. They say, what, yeah, let's do 35 because that's where our groupings is reasonable. But for your data set, whatever that is, right? Again, nobody can tell you what it is, but WSSC can tell you, it can sort of point you to a region. I can say, yeah, your optimal K is somewhere around here. So usually we are going to start with that, and then sort of inspect the data and sort of figure out, okay, what's the optimal K for our data is. Right, this is a big distinction, right? So remember, and this is the big departure from our supervised learning. In supervised learning, if we ask you, guys, what's your training accuracy? You will say 68.2. There's a number, right? There's a very different number. Right here, it's a little fuzzy. Does that kind of make sense, guys? Kind of, right? The very different way of doing things. Yeah. All right. So, any question on this one, guys? So K means we understand, right? Let me see. All right. So, how do we find the best K, right? Basically, we find the elbow region. Yeah. So, good, guys. So let's see what else. So let's kind of, again, like I said, K means very simple algorithm, right? But it works really well. So strengths and weaknesses. K means is simple, well understood, because all we are doing is calculating the distance between points and moving the center points around, right? Very simple math, right? And you can verify pretty easily, right? Remember when I looked at the car data, right, back here, when K came back with a bunch of groups, I can inspect the data and say, oh yeah, this grouping makes sense to me, right? So we can verify K-means very easily. Right, that's another thing.
So do you think by somehow not plotting but actually calculating, say, all these points of k numbers
Mhm.
of things, and we try to find a spot where the slope for one point and another goes to -1/3, for example, like
Oh, I mean, here your error is going to be, positive, right? So positive number going to come down, So the typical pattern
I'm
you're
just
looking
looking
for.
at the slope. I'm looking at the slope here,
Oh, yeah, got you, yeah.
connecting two lines, and I'm thinking on
Yeah.
-1/3
The
looks like
gradient, right?
yeah.
Yep. Well, so here's what, right? So again, remember, this is just a starting point. This is like one metric you're going to consider to say, okay, here's how my error behaves, right? And then you will use other, other consideration, like, and these are like usually, very domain specific to say, okay, let's say, from here, your K is anywhere, you can say, what, my K can be anywhere from, 5 to 8, 5, 6, 7, 8. Which one is the best K? Now you need to bring in some other metrics that are specific to your data to sort of narrow it down. Because just looking at WSC alone will not give you that, right? And this is a weakness of K-means. Like K-means cannot give you the optimal number of clusters. Because K-means can go find as many clusters as you want. Remember the example we did earlier, right? Same data, I asked K-means to say, go find me 2 clusters. Sure, it's happy to go find 2 clusters. Same data, go find me 3 clusters. Sure, it will find it, right? So K-means can find as many clusters as you want. But how many clusters make sense for your data? That you have to sort of include some other metrics that are specific to your domain to make sense. So hopefully gave you some ideas, right? Again, if you ask me, like, for example, the Walmart example, right? They looked at the data and they said, yeah, you know what, we want our K to be 35 because that made sense for them, right? For their business domain. For your data, it'll be something else. And as you guys do your exercises, you kind of see, right? There are different metrics you will use to figuring out the optimal K, right? So hopefully that made sense. And this is the part of one of that determinant K means, like, it cannot tell me what is the optimal K is. K means will go find as many classes I wanted to find. So, and this is where the bit of a human interaction, human kind of how do you say human gut feelings and then domain knowledge comes into picture, because using that you can figure out the optimal number. Okay. Outliers can bias results. Remember, so we know this by now, right? Because if we look at the right, if we imagine your data is going to spread out, and the Stanford example is a pretty good example, right? So here, right, we have a lot of outliers. So these are the actual core groups, right? But we have outliers too, right? So outliers can sometimes pull the center out, right? So how do we fix this? Very simple. What we do is, we actually, before we even do k-means, we remove the outliers. Remember the house sales data, we looked at quite a bit. There are a lot of outliers, right? They're like, these big bedroom houses and all this house, right? So let's say you're trying to find a grouping of the house sales data using k-means. So what you would do is, before we do k-means, we'll remove all the outliers. So we'll say, what, we're not going to consider 33 bedroom houses. We're only going to consider bedrooms that are, less than 5 and 5 and under, right? So what you're doing is, and how did you know this? Because we know the domain, right? Because we know, okay, most houses are, I don't know, 5 bedrooms or less, right? Not 33 bedrooms. So now we are using our domain knowledge to kind of, clean the data and then running k-means, right? So yeah, right? And also, like, sometimes k-means will not converge quickly, right? So it's called, you remember k-means iterate over the data many times, right? Each iteration it does, you can see the center points kind of moving around and finding. Usually it's pretty quick convergence, but sometimes the center points will bounce around. Just remember, right? I mean, they're using the same, minimizing algorithm, and sometimes they don't find a solution, and that's fine. So what we do is we do multiple random runs. So if one run kind of gets stuck, that's okay, right? We'll do multiple runs, and so kind of converge. So even though some of the weakness of k-means, right, is not the ideal algorithm, but we can actually overcome these pretty easily. right? These are not deal breakers, and that's why k-means is very popular, because even though it's a simple algorithm, it can work pretty well, right? All right, guys. So, and then I'll just another word about hierarchical clustering very briefly, and then we will wrap this up. Remember unsupervised clustering algorithm, we looked at k-means. The other one is called hierarchical clustering. So the way hierarchical clustering does it, like, it kind of goes like this. Let me show you guys this. It creates an upside down tree, right? And these are called dendrogram, right? So, and here you can see, right, it's it's basically keep dividing the data until it, basically, you can get like individual leaves. Then just like a tree, we can prune this dendrogram at any level. So let's say I only want 2 clusters, right? I just prune at this level. And then I have only, everything's kind of folded into these 2. If I go a little deeper down, right, when I prune this here, right, now I have 3 clusters, 1, 2, 3. So let me just write here, right? 2 clusters, here you have 3 clusters, right? So you can choose the level in a way we want to kind of go and, slice the tree. So the deeper down we go, the more clusters we have. Same idea of k-means, right? But here, it sort of basically pre-calculates all the splits beforehand, and then we choose the pruning point. Right? So it's a little enhancement on dendrogram, a little better, right? So for our purposes, we are going to be using k-means for our labs. But I'll put some links. You can go look at the dendrogram-based clustering as well. Right? Good, guys. All right. So clustering in Python. Let me show you guys the k-means are in Python real quick. Right, again, in scikit-learn, cluster k-means, right? So what are we saying? Basic parameters line, this is how many clusters to find, right? Remember, in k-means, we have to tell k-means to find, how many to find, right? And that's pretty much it. And maximum iteration basically, right? Remember, it iterates over the data. Sometimes, it doesn't converge. So we are saying, don't go beyond this, right? Otherwise, you're gonna get into like infinite loop situation. So we are saying, right? Don't go beyond that. Right? So k-means. Let me show you a full example real quick. Right. So here's my data set. I'm reading my cost data set. Right. And basically we are calculating my feature vectors. Just remember, just these 2 columns, MPG and cylinder. That's it. Right. So I'm extracting that. That's it. Here's k-means. Right. I say k-means, go find me 2 clusters. Right. And fit. Right. And then WSSC is basically predicted using it's called the Jacobs inertia. Right. So you'd say, wait a second, why am I not doing train test split? Anyone want to know why there's no train test split?
Based on what values?
It's clustered.
It's clustering, exactly. Right. So remember, this is unsupervised. There's no training. Right? Exactly. So that's why we don't split the data. We give the entire data to k-means and say, right? So here, fit feature vector, right? The entire data goes in. Yeah. So this is different than everything we have been doing, right? Remember, every lab we are done, we sort of first thing we do is like we calculate our test and train data. But here, we just give the entire data set and then say find patterns, right? That's it. So
I could think an example. We see signal, electronic signal, whatever, from an interstellar space. Okay.
I'm gonna cluster. Okay, I got you. Okay, go on.
Things are coming in continuously. We don't know if they are actually bytes or if they are bits or what they are. You try to register them somewhere, and then you try to understand if they have any structure.
Any pattern.
Probably you'll try to do any clustering to see, do they have any patterns? Do they not?
Yep. And those are perfect, right? Because at this point, the data you mentioned, there's no like input and output. It's just data, right? So what you're trying to find is any pattern. So yeah, so that's where the clustering algorithms can help you to say if there's any pattern. Because what they do, right? Because they try different groups. And here's an example of Remember we said, we don't know how many, what the ideal K is, right? Very simple. What we do is we iterate over multiple K ranges. So you can see right here, I'm doing like a little for loop, right? I'm varying K from 2 to 17 or something, right? And for each K, and I'm initializing K means I'm saying set K equal this, right? Yeah. And then just fit. So what I'm doing is for each K, I'm printing out the WSSC, right? And then I think I have a graph on, there we go. And then sort of plot the graph. You can sort of see here, right? And then we get an idea of WSSC, K and WSSC. And basically any algorithm you guys use, right? What you should pretty much is like the error should come down pretty rapidly and then kind of, stabilize, right? And then kind of, we look at the elbow region and say, okay, what could be, my K could be somewhere around here. So in K means, right? So even though it's basically, right? We don't, how do you say? We don't know the exact K. It's very simple. We just do like a little loop, right? Go through a few and then, do a plot and then see, where our optimal K is. Yep. And then there's no training, right? Because, basically, at this point we are, because the error metric only gives you an indication. It doesn't exactly tell you, okay, the right, K is 6. That's up to us to make the decision, right? That's for the human in the loop. Good, guys. All right. So any question on this one? Kind of, it doesn't make sense. Again, if you look at the code, right? This code is, pretty trivial, right? Just a few lines of code, initialize K means, and then just fit. And we fit the entire data, entire vector. And this K, scikit K means there's a variable called inertia. That is the error, WSSC, right? So, and the idea here is kind of, right? Each time you do this, but as I increase K, K2, K3, K4, right? The error should keep it coming down. And if you sort of plot this, it'll make sense in the plot, right? So here's K and WSC, you sort of do the plot. Okay. Oh. Good, guys. Any questions on this one? So very different, right? Very different than what we have learned so far. Because if you look at the algorithms, right? So we did the right, we did the like supervised algorithms. It's like a formula, right? We get the data, we massage the data, we clean up the data, and then we split X and Y, right? Run the algorithm, cross validation, all this, right? But here, there's no training, there's no explicit training step, right? So very different algorithm, right? So. All right, guys, so let's do this. We are kind of, we are almost at the time. So here's the plan, right? For this week, again, you guys can tell me how you want to do this. We can take this easy on this week, or, we can sort of start with K-means. I will add some reading material for you guys, right? For in our right in our guidebook. And two things. I'll also put the lab as well. So we're going to do 2 labs here. One is the cost data set we have, right? Empty cars. And the other lab is pretty cool. It's basically Uber trips, right? I will, clustering, Uber pickup points. So that's a pretty cool, I'll upload the notebooks for you guys. You can start working on them, okay? So those are 2 K-means labs. Also, you can start looking at, like, for example, if you're in UCA repo, right? Repo, right? And you can look at the data sets. See, you can start looking at clustering data sets, right? See, clustering, now, now we are done classification regression. Now we are going to clustering. So start looking at some data, data clustering, and maybe find one that you guys like, right? That's again, some of these are kind of right. You got to kind of really read and understand what the data set is like, right? So like here's like an online shopping, could be interesting, right? They're trying to classify what kind of a shopping patterns you see, right? Things like this, right? So anyway, yeah. So look around. You'll see a lot of numeric data because clustering tends to be like a lot of numbers, right? And maybe pick a data set. And so this one I will also, I'll give you guys one data set to kind of go through, but then, I'm going to have you guys pick your own data set because, that's kind of part of the challenge too, right? So you get comfortable with your own data set. All right. And then there'll be this lab for this week, guys. So do you guys want to meet next Saturday? What's the consensus? What are you guys thinking? Or should we do like a, yeah, again, up to you guys, right? Because I do want you guys to also do the, right, catch up on the tree algorithms, right? Because the tree algorithms are very important. So, right, because those are the ones that are going to help you, especially when you do like production scale, classification regression, like random forests and exposed trees will definitely help you guys, right? So I want to make sure you guys had a chance to work on those as well, right? Okay, so let's do this. I mean, K-means is pretty straightforward, guys. So yeah, the let's do this. Here's a plan, right? I know, because if we take too many breaks, here's what's going to happen, right? Because it'll just keep dragging on, and then we'll never finish this track. So here's my plan, right? We have a couple more algorithms. Let's go through them. Then, depending on our appetite, we can actually come back and do some revisions, right? So this way it kind of keeps moving on, but at the same time, we can still keep some time towards the end to revise and do some projects. Is that going to make sense? I think this way, we don't keep dragging on it, because I know holidays are coming December, because I don't want to December we'll definitely take a break, right? Towards the last 2 weeks of December, because everyone's, Christmas and New Year's and all that, right? So let's kind of squeeze in classes as much as we can. I guess with me, yep. And again, if you're a little behind, again, that's part of the game, right? I mean, that's fine. We understand. Try to catch up as much as you can. Yep. All right, guys. So let's plan on meeting next Saturday. Okay, unless something changes. So, and then also I'll update the update the reading material for you guys. Also, one more thing. For the final project, we want to do like at least 2 or 3 projects. Like for example, I want to do like 1 regression project, 1 classification, and 1 clustering project. And these I want to kind of get some real world data. And this I kind of want you guys to see if you can do as a group project. I think it'll make more sense, right? Because the projects are going to be a little harder. And so thinking about some group, picking a partner. So maybe like groups of 2 or 3, up to you guys. You can choose. We are still a few weeks away, so no rush. But I kind of want you guys to start thinking about this and say group project, because we want to do this early on, and then we can also defer that. So for the final project, let's do it as a group project. And I think that'll be good. That'll be a good way for us to all to kind of come, finish this track. All right, guys, that's it. So let's meet next week. I will send out an email or Slack once I have the reading material for you guys, and then we'll go forward. Yeah. Good. All right, guys. Anything else? Perfect. Thank you. So keep an eye on the email. Yep. Thanks, guys.